Hello everyone, my name is Neder and today I'll be presenting the project that my colleagues, Arthur Nardi, Santos Machado, and I have developed over the past year. The title of our presentation is Short Period Pitching Control Modeling and Design using Simulink and FlightGear. Initially, the problem we address is based on the fact that the increasing complexity of fly-by-wire systems necessitates accurate models and controlled simulation environments. This includes, for example, complex control laws, flight envelope protections, integration with other systems, and fault tolerance. To address this, our work focused on the design and modeling of short-period pitching control for the Airbus A320 aircraft. The primary reason for selecting this aircraft was the public availability of the necessary information, variables, and the operational behavior required for the designing the control system and for its validation using flight gear. The initial challenge was modeling the flight mechanisms associated with the aircraft behavior in the flight. The equations of motion governing the dynamics and kinematics of the A320 are highly nonlinear, coupled, and multivariable. The specific aerodynamics parameters are derived using the DATCOM software based on the aircraft geometry. The control system design for the longitudinal loop of the Airbus A320 is designed using modern control theory, combining a linear quadratic regulator (LQR) with a Kalman filter based state estimator. Finally, to validate the developed model, its open loop dynamic response was compared against a high fidelity benchmarking using the commercial flight simulator X-Plane 11. This simulator was chosen because it features an official licensed aircraft Airbus A320 new model, whose flight dynamics are based on the real aircraft qualification test guide, ensuring a high degree of realism. The equations of motion are nonlinear, coupled, and multivariable. For the plane's modeling, these equations are simplified into a short period model suitable for attitude control. This is done to isolate the state variables, which are the rate of angle of attack, alpha dot, and the pitch rate, q dot. This simplification allows the study to focus solely on variation in the aircraft's longitudinal attitude. Using DATCOM, the geometry of the A320 aircraft was modeled based on the flight manual data obtained for our references. An approximation of the aircraft airfoil was implemented to simulate the true aerodynamic configuration of the wings and the horizontal tail. The result obtained for this process is the specific aerodynamics parameters, which are used to fit the plane's model. For the model linearization, an operation point was chosen corresponding to a steady level cruise flight. This point is defined at the altitude of 14,000 feet, an airspeed of 168 meters per second, and a weight of 65,000 kilograms. The equilibrium point, or trim, was calculated using the object-oriented Python routine utilizing the finite difference method. The routine returns the continual time-state-space matrices A, B, C, and D that define the aircraft's longitudinal short-period dynamics, where the C matrix is the identity matrix and the D matrix is the new matrix. The model validation was performed using the X-Plane 11 software. The validation procedure involves replicating the exact same flight condition in both the custom Simulink model and the X-Plane simulator. An altitude of 4,267 meters, a speed of 168 meters per second, and a mass of 65,000 kilograms. This is the same trim point chosen for the model. To ensure a direct and fair comparison, the aircraft in X-plane was configured to directional low mode. This setting bypasses the flight control computers, allowing the pilot's inputs to command the control surface directly, thus create a raw open-loop response analogous to the Simulink model. The system's dynamics were excited by applying a sustained maximum elevator deflection to induce a pitch-up maneuver. The result time history data for the pitch angle and pitch rate from both simulations were then compared, thereby validating our nonlinear plane against the X-plane 11 commercial simulator for the same aircraft and operating point. The design requirements for our control project were a peak time of less than 1 second, an overshot of less than 45%, a settling time of less than 3 seconds, and a zero steady state error. The actuator saturation was modeled to impose physically possible limits on the elevator deflection and throttle position. The elevator in this case can deflect from minus 30 degrees to 20 degrees, and the throttle inputs varies from the 0% to 100%. Our simplified block diagrams consist of a controller and an estimator which together provide the elevator deflection angle and throttle position to the plant, which represent the aircraft's dynamics and kinematics. The plant, in turn, returns the angle of attack and pitch rate to the controller and estimator. Measurement noise enters the controller and estimator block, which must follow the reference values to achieve zero steady state error. The proposed architecture follows the separation principle, in which the controller and estimator design can be performed independently. The complete system is composed of LQR controller with reference compensation, state estimator, actuator saturation, and plant model. The implemented control law follows this structure, where U is the control input vector, R is the reference signal, KR is the reference compensation gain, K is the LQR gain matrix, and X is the estimated state vector. For digital implementation, the continuous time model is discretized using the testing method with a sample time of 0.001 second, resulting in a discrete state space model suitable for implementation in digital control systems. For the LQR design, the Q and R matrices were determined iteratively to meet the control requirements. The Q matrix is weighted to prioritize control of the angle of attack over the pitch rate, and the R matrix penalizes the throttle more than elevator, as the elevator has a more significant impact on the angle of attack control. For the Kalman filter, although all states are measurable, measurement noise motivates the use of Kalman filter, suitable for linear systems with Gaussian noise. The Kalman filter design requires defining the process noise covariance matrix and the measurement noise covariance matrix, based on the characteristics of ADIRS, Air Data Inertial Reference Systems sensor typical in commercial aircrafts. Matrix QK represents model uncertainty, while RK characterizes measurement noise from the sensors. The LQR gain was obtained by solving the algebraic Riccati equations, yields the controller gain matrix and the reference compensation gain. The optimal Kalman filter gain is obtained by solving the algebraic Riccati equation through the estimator and then it's computed. The Kalman filter was tested by applying white noise, and it was verified that the filter provides a smooth state estimation effectively filter the measurement noise as shown in this graph. The design LQR controller and Kalman filter were integrated with the continuous time nonlinear plant model to evaluate the closed loop performance. The simulation was configured for a reference step input of angle of attack equals to 10 degrees, with actuator saturation limits for the elevator set to 17 degrees in a simulation time of 20 seconds. The response of the nonlinear systems was compared to that on the linearized model for which the controller was designed. The results show a very close correspondence between the two responses, with the nonlinear system exhibiting a stable response with a low amplitude oscillation around the reference value in the steady state. The design system successfully met all performance requirements. Furthermore, the controller effectively stabilized the pitch rate, which remained bounded and settled quickly, in contrast to its unstable behavior in the open-loop configuration. A key requirement for flight control systems is robustness to variation in aircraft parameters. To this end, the controller's performance was evaluated under a significant change in aircraft mass, simulating fuel consumption during flight. The simulation was repeated for a reduced mass of 60,000 kilograms, down from the nominal 65,000 kilograms. The result demonstrated that the controller is robust to this parametric variation. The system response for the 6,000 kilograms case was nearly identical to the nominal mass case, successfully tracking the reference and meeting all transient and steady-state performance requirements. This confirms that the design controller provides consistent and reliable performance across a range of operational conditions. In conclusion, methodology success. The LQR and Kalman approach successfully demonstrate the reliable and scalable aircraft controller design methodology, validated by simulation. Future direction. Work is required to overcome linear model limitations by expanding to full 6 degrees of freedom control, robustness analysis, and incorporating nonlinear or adaptive control for large deviations. And this is reference which we base our working on.